Hello everyone, welcome to our work, Self-Guided Diffusion Models. This is joint work between me, David, Yuki, Gertjan, and Snoek. In traditional diffusion models, there's a concept named guidance. And to achieve guidance, there are two main pipelines named classifier guidance and classifier-free guidance. Even though they can achieve different guidance schedule, but they still rely on heavily annotated data. In this work, we are trying to remove the necessity of the annotation by utilizing the development and of self-supervised learning. We design a framework named self-guided diffusion models so that we can achieve the almost the same fidelity in comparison with the baseline by utilizing the labels. And our method is simple and flexible and potentially scalable to more larger scale data set. So firstly, I would like to introduce the motivation of why guidance are needed in generation. Firstly, conditional generation is more realistic than unconditional generation. And secondly, conditional generation can lead to higher fidelity in comparison with unconditional generation. And finally, the guidance in generation can provide us the flexibility to control the generation by strength, modality, and granularity, etc. So the second motivation is why self-guidance in generation. Firstly, because label annotation is very time consuming. And secondly, because self-supervised learning is very annotation free, and it's pity if we don't utilize it. And finally, it could be a potential bridge to translate the progress from the community of self-supervised learning to generative modeling community. So here we provide an overview of this talk: method, experiment, and conclusion. Firstly, I would like to introduce two basic guidance methods in diffusion model. One is classifier guidance, but for classifier guidance, typically they need to train extra classifier, so it's not classifier free. And most importantly, it still need the data annotation for the extra training of classifier. And for classifier free guidance, they utilize the ability of conditional sampling and unconditional sampling in a single model. So by that way, they can achieve classifier free guidance, but they still need the annotation to finish the training. And in this work, we propose a self-guidance that can be classifier free and also can be annotation free by utilizing the self-supervised learning. So here we propose a method named self-guided diffusions. Our method input is image without any annotations. And our method is composed of two parts: self-annotation function and self-guidance function. For self-annotation function, we can utilize the advancement of self-supervised learning to generate different granularities of guidance signal. For example, image level guidance, bounding box level guidance, and pixel level guidance. When we obtain those guidance signals, we can inject them into the function of self-guidance. By that way, we can generate samples which is totally respect the guidance signal, for example, cluster ID, bounding box, and pixel level guidance. And in detail, in self-annotation function, we directly utilize k-means based on a pre-trained self-supervised learning backbone. By that way, we can get a one-hot cluster ID embedding and use them as a condition. For bounding box and pixel level guidance, we use previously a method named lost and stagger. By that way, we can inject those signals into our diffusion framework. And here we notice that other choices should be also suitable for our framework. So in general, the training and sampling process are almost the same with GDPM. And for training, given time step, we predict the noise they use to predict the noise. And for sampling, given time step, we predict the mean and variance and do the sampling gradually. And there is a weight named the guidance strength that is used to balance the diversity between condition and unconditional sampling. In total, our framework is simple and flexible, and they are potentially scalable to larger scale dataset. For method part here, we mainly introduce how we inject the guidance signal in 3 different granularities. For example, image level guidance, we directly send them into MLP and add them with the time embedding and sum them together and send them into every block of the unit. For unit with for guidance of the box and pixel level guidance, firstly we flatten the feature and send them and do the same tricks and send them into every block of the unit. And for the spatial signal, we also concatenate with X. By that way, we have 4 channels for the unit, and we also tokenize them and send them into the block of the unit by cross attention. So here we first displayed which kind of backbone is suitable for extracting those self-guidance signals. And we find that Dino achieved a better trade-off between FID and the exception score. And also we're trying to find the indicator which is potentially helpful for us to pick out the most suitable backbones in those tasks. And we found that NMI is a kind of a proper metric help us to pick out a suitable backbones. And here we show the main results on image level guidance signal. We can find that by utilizing no guidance, the result is quite bad. And when we utilize the human level guidance, we can indeed see a much more better performance. In our image level self-guidance diffusion model, we can see when we gradually increase the K of the K-means, we can find a sweet spot, which is 5,000. Which means by that way we can achieve better performance in comparison with ground truth label guidance. And in this table we draw the same conclusion as previously. And we also did the same experiments on larger resolution image, which is, for example, image 100 and the F-sun churches. We saw the same phenomenon. And here we visualize different clusters of condition. Different samples conditioned on the different clusters. We can see that different clusters, they indeed represent different color and style of the churches. And here we show that given the original image and the bounding box, we can generate, for example, 7 very diverse images, which is totally respect the location of the bounding box and the shape. And we draw the same conclusion as the image level guidance. We can see that our self-box guidance are much better than ground truth level guidance. But indeed, when we utilize the ground truth box guidance, we see an oracle results where we still have a gap between them. And here we see that by utilizing the original image, we can generate this kind of segmentation mask by free, and we can generate 6 diverse examples, even though the unsupervised segmentation mask is quite noisy, but our diffusion model can still perfectly recover the noise. And here we highlight that the meaning of different clusters. We can see that different clusters indeed have different semantic meaning. For example, brown and white dog, or dog with white fur, and etc. And here we visualize the pixel level guidance. We can see that when we sample many images, we can see different samples indeed share many common semantic meaning. For example, giraffe, sky, and tree. And here, when we gradually increase the guidance strength from 0 to 3, we can see that our color is more saturated, and also they are more close to the pixel level guidance. And here we show that when we condition those segmentation masks, we can generate very diverse images. To conclude, to achieve a high fidelity, we need a human annotation to provide guidance. And to avoid annotation, We obtain those guidance signals of 3 different granularities by free. And based on it, we design a simple, flexible framework to solve the problem. And if you're interested in your work, feel free to come by our poster or send me email. Thank you.